Hello, this is Jack Jackson. In this video, we're going to introduce triple integrals, specifically in rectangular coordinates. Well, once you have the idea of a double integral, conceptually it's not too hard to extend that to triple integrals, or if you wanted to, 4, 5, or 6, or 7 integrals. So let's just kind of look here side by side at what's going on. So let's review, first of all, signal integrals. The domain is a one-dimensional interval, say the interval from A to B, or x1 to x2, along the x-axis. We subdivide that into n subintervals of widths delta x sub k. Each one has its own width. Oftentimes we let those all be the same, but we wouldn't have to do that. We pick some x sub k in each of those intervals. X sub k in the kth interval, x sub 1 in the first interval, x sub 2 in the second interval, and so forth. And we evaluate the function at that point to get f of x sub k. We multiply the f of x sub k times the delta x, and this gives us an area of a subrectangle. Its width is delta x sub k, and its height, or signed height, is f of x sub k. So when I say area here, I probably should say signed area. And then we sum the areas for a Riemann sum. So we add those up for each of these sub intervals, yielding an area of a subrectangle. And we add those up, and this gives us an area estimate. Take a limit now as the number of rectangles or number of subintervals goes to infinity, and the widths of them go to 0, and that becomes the definite integral. Okay, that's what we did back in Calculus 1, did that a lot in Calculus 2 as well. And we extended earlier in this unit to a double integral. Now, instead of the domain being a one-dimensional interval, it's a two-dimensional rectangular region, say x going from A to B and y going from C to D in the xy plane. We divide it into sub-rectangles, sub-rectangular regions, and we have the area of delta x a sub k for each of those ones. We could make them all the same, in which case delta a sub k's would all be the same, or we could make them different. We evaluate the function at a point in each of these. So in the first one of these little rectangles, we find an x1, y1 somewhere in that. Could be at one of the corners, could be at where the diagonals crossed in the center, or some other place. It doesn't really matter, but find the f of there. So that's going to be we're going to interpret that as a height. So we multiply that height times that area of that base, the area of that rectangle, and then now we have this product, f of x sub k, y sub k, times delta a sub k, and that's a volume of a prism, rectangular prism. We do this for each of these little rectangular subregions, and we sum these volumes to get a Riemann sum approximating our integral. Now take the limit again as the number of those pieces. In this case, the pieces are rectangular subregions, and when we multiply, we get volumes of rectangular prisms. We want the number of those to go to infinity. And the widths of those, the delta a sub k's, not the widths, but the base areas, to go to 0. Once we take that limit, that's a double integral over our domain of f of xy dA. Well, if you understand that, it's not a big step to go to triple integrals. Now, instead of a 2D rectangular region, we have a 3D rectangular solid prism for our domain. For example, x could go from A to B, y from C to D, and z from E to F. This is an XYZ three-dimensional space. So, what do? We divide it up into n sub-rectangular prism pieces. Each one has a volume of delta V sub k. We could do it again in such a way that all those are the same, but again, it's not necessary. Find a point x, y, z, x sub k, y sub k, z sub k in that kth prism. Again, it could be at one of the corners. It could be where the diagonals cross in the middle. Could be anywhere in there. But take that and evaluate the function. Okay, so multiplying that by the volume gives us a fourth dimensional hypervolume. Maybe hard to visualize, but it's pretty easy to compute. And it's not actually it's subrectangular. Probably I should call this a hyperprism. Okay, because it's actually a fourth dimensional object, but who cares? We can find this number, whatever it is. So you sum these things for your Riemann sum. So you've got your f values times your delta v's, and you sum those all up. That's your Riemann sum. Now, again, take a limit as the n goes to infinity, and those delta v's go to 0, and we have a triple integral. So it generalizes very nicely from what we've done in 1 and 2 dimensions. And of course, you could extend this to even more integrals if you wanted to. Typically, we study double and triple integrals in Cal 3, and we don't go beyond that, but in theory, there's no reason why this couldn't extend further. Now recall, for double integrals over non-rectangular regions, we defined a new function that agreed with the original function on the original domain and defined it to be 0 outside the domain. Then we integrated this new function over the rectangular domain, which included the original domain, to find the double integral of the original one that we set out to do. So similarly, for triple integrals over a region of space D, the domain, which is not the interior of a right rectangular prism, we just defined a new function that has the same values as the original function on D and 0 everywhere else. So then we define the integral of the original function over D to be the integral of the new function over a prism that's big enough to contain all of D. So it generalizes the same idea very nicely, and we can still use our setup on the previous page. Okay. So we have double integral, our domain of f of x, y, z dv is the limit as n goes to infinity of delta v sub k goes to 0. The sum of k equals 1 to n of f of x sub k, y sub k, z sub k, delta v sub k. Okay. And I guess technically this could be some function g that agrees with f on the domain. And then this is divided up so that it covers the whole thing. So like double integrals, triple integrals can be interpreted as iterated integrals. In rectangular form, the volume differential is dv equals dx times dy times dz in any of the orders. If the domain is in the interior of a right rectangular prism, say going from A to B on x, c to d on y, and e to f on z, then you could integrate in the order x, then y, then z. Dv becomes dx, dy, dz. The first integral goes from a to b for x. The second integral with respect to y goes from c to d. And the third integral goes from e to f on z. And if you switch the orders, you just have to make sure these things go with the right one. So for example, if you switch x and y, you'd make sure this one goes from c to d for y first, and then a to b for x next. In 2 dimensions, when you have just dx and dy, there's just 2 orders. In these, there are going to be 6 orders. Okay, dx, dy, dz, dx, dz, dy, dy, dx, dz, dy, dz, dx, dz, dx, dy, dz, dy, dx. I think I said all 6 of those. Now, for a more complicated domain, remember, we set up a triple integral as iterated integral with variable limits on the inside of the integrals, just like we did for a double integral. Now let's suppose that we're going to integrate with respect to z first, then y, and then x. Now suppose that z, the region is such a region so that if we took a plane and moved it from a lower z to higher z, that within the domain, that you would start at some function z1 of xy, and it would go up to z2 of xy. In other words, the top and bottom of this are given z as a function of x and y. If so, then you can integrate with respect to z first like this. Whatever this function is as you're integrating goes here. That really doesn't have anything to do with the domain itself. That's the function you're integrating, the integran. The domain has to do with these limits. So here, our lower limit is given by some surface, z1 of xy, and our upper limit is given by z2 of xy. Notice these are functions of x and y. They won't have z in them, but they'll have formulas that have x and y. Now, when you integrate all that, you're going to get you integrate assuming x and y are constants, and z is your variable. Then you substitute these things in place of z and evaluate using the fundamental theorem of calculus. So you have your partial antiderivative with respect to z and evaluate that, just like we did with double integrals. And this way, when the dust settles on this first bracket here, you get a function of x and y only. There's no z's involved. Now we're back down to a regular double integral. So the y's then run from a lower y as a function of x to an upper y as a function of x. Now what we actually do is we take our region, whatever it is, and we project it onto the xy plane, like make a shadow. And whatever shape that shadow is on the xy plane is going to be what we use to determine our limits here. Okay, and at this point, if we assume that this region is such that if you draw a vertical strip going from a lower to an upper part, the lower part is always going to be bounded by this curve y1 of x, and the top is always by y2 of x. So these are formulas that have x's in them and not y's. This formula here, once you've gotten rid of this bracket right here, replaced it by a formula that has x's and y's in it, do an antiderivative with respect to y, partial antiderivative, evaluate at these two endpoints. Now your y's are gone, you have a function of x. Now take this shape that we projected onto the xy plane, project it onto the x-axis, and see that x only goes from one constant to a constant. So you have your first integral, your innermost one is done first. It's going to have a function of all the variables. You'll have the z variable, if that's the one you go with first, will be, these are limits in terms of z, but they're limits for z, but they're in terms of x and y only, so no z's here. Then the next one, you're going to only have one variable there. You've eliminated z, now you're going to eliminate y here. These are limits for y, but they are in terms of x only, and the last ones will be constants. Now we usually suppress the brackets here and just write it like this at the end. So regardless of the order of integration in a triple integral, the first or innermost integral will have limits which are functions of the other two variables. The second integral will have limits that are a function of the last variable, and the last integral will have limits which are constants. So let's do an example. Okay, if the integrand is the function f of x, y, z equals 1, then we can interpret the integral as the volume of the domain. So it's a way we can do the volume as a triple integral. If the integrand is the density function, I'll call it delta of x, y, z. Some people use rho there. I'm going to try to avoid that because I'm going to use rho for polar coordinates a little bit later on. So I'm just going to call it delta. Then we can interpret the integral as a total mass of the solid, if we have that. So here's our example that we want to do. Find the mass and average density of a solid that's bounded by the surfaces below, where the density is given by 4x. So we have this 3D solid bounded by the surfaces below here. If you'll notice, all four of these things are planes. A couple of them are real easy to see. Z equals 0 is just the xy plane. X equals 0 is just the yz plane. This is a line in 2 dimensions. So this is just a plane going straight up from that line. It would intersect in the xy plane, and then that's a kind of a slanted plane in 3 dimensions. So when these planes all intersect, there are 4 of them, we actually get what's called a tetrahedron or a triangular prism. And well, it's in the first octet. Let me show you what it looks like. Hopefully you could maybe visualize it looking something like this. On the bottom we have the xy plane. On the back side over here we have the yz plane. By the way, the red axis coming towards you is the positive part of the x-axis. The green one going to the right is the y-axis. And the positive part of the z-axis is blue. It's going straight up. And so we get the back part of this is on this plane where x is 0. That's the yz plane. The bottom is on the plane where z equals 0. That's the xy plane. If you look at this line right here in the xy plane, that's the line 4x plus y equals 0, if it would extend it on, and you go straight up from that. So that's perpendicular to the xy plane. And then this other plane comes in and kind of slanted for this other face here. So this is called a tetrahedron. Tetra is 4. A polyhedron is a solid that has faces all made up of polygons and their interiors, and then you make it solid, so we're going to do all the inside of that. So that's what it looks like. Now the density is changing. It changes with x. So when x is 0, the density is 0. So it's actually density 0 right along the yz plane over here, and it gets more and more dense as we move out toward this corner over here as x increases. All right, now we need to find the corners here, the vertices. There are 4 of them. And to do that, we're solving where 3 of the planes meet. Where 2 of the planes meet will give us lines, like say that would be the lines containing these edges. We might want those later. But if we want to find the vertices there, we want to find where 3 of the planes intersect. So I just take these 4 planes. There are 4 sets of 3 of those. Solve that system simultaneously, and we get 4 points. So, for example, if we take the last 3 here, well, first of all, I did something else too. 4x plus y equals 0 is the same thing as saying y equals 1/4 x. That's not correct. Let me fix that. Actually, I want y to be 1/4 x, so I'm going to go back to the original problem here and change this to x minus 4y equals 0. Of course, you know, when you're the teacher, you can say, oh, I don't like that problem. I think I'm just going to go change it. Unfortunately, you don't get that option on exams most of the time, right? When you're the student. But here we go. So now y equals 1/4 x. That's what I want. Up here, we solve for z. Let's see. We're going to add the opposite of these to both sides and divide both sides by 4. So you get negative 3/4 x plus negative 3y plus 6 equals z. Okay, I believe that's correct. Of course, these are already solved in a nice way. Okay, so let's use these forms of it and solve these. So if we take these last 3, y equals 1/4 x, x equals 0, and z equals 0, we see that when x is 0, we see that y is also 0. We already have z is 0, so we get the point at the origin. So that's one of the corners, one of the vertices. Let's go down here next. This one, I took the first one and the last 2. So here, if we have x and z are 0, we substitute in 0 for x and z. Let's see, this says it says 0 equals negative 3y plus 6, so that gives us y equals 2. So that's 0 to 0. That's this vertex right there. Okay, you can kind of see the 3 planes, the slanted one, the back one, and the bottom one intersecting there. All right, up here in the upper right, let's see, what do we have? We have the the slanted plane here, the plane on this side, and the one at the bottom should intersect at this point here, 4, 1, 0. Let's see if, let's see. That's this one down here. Yeah, let's do it next. Okay, so we have, that's the top equation, the next one, and the bottom one is equals 0. So anyway, to work this out, I'm going to plug this in. So I'll plug in 0 for z here, and I'll plug in 1/4 x for the y here. So that's negative 3/4 x minus another 3/4 x is negative 6/4 x, which is negative 3/2 x, and then we got plus 6. So let's see, I want to add 3/2 x to both sides, then multiply both sides by 2/3. 6 divided by 3 is 2 times the other 2 is 4. So we get x is 4, and then I plug back in here to see that y is 1. So we got x is 4, y is 1, and z is 0. That's this point here, 4, 1, 0. Okay? And let's see, this one here, this is the last one. So this is going to be the point, this is going to be the point up here at the top. So you take, we're on this plane here, which is the second one. We've got x equals 0, but we have a variable, we have the z here. So let's see what happens. We have this plane here. So it's this top, this slanted plane, this plane, and then the back plane. But we're not necessarily down here at the bottom anymore. Now we're going to be up here higher. And let's see what happens. So again, we plug those in. 0 goes into the x, makes y 0. And then y and x of 0 go in here, and we get z is 6. So that's 0, 0, 6. All right, so now we have our vertices. We have our formulas for our different surfaces. Now we want to set up the integral. I'll go ahead and set up the integral for the volume and for the density. They're very, very similar. Okay. The first thing is we're setting up the volume formula. The volume is the integral over the domain of dv. So we're just integrating the function 1 here. Now, the way this is set up, no matter where we are at the bottom, if we go straight up, we're starting at z equals 0, and then we're going up till we hit this slanted surface, this z equals negative 3/4 x minus 3y plus 6. So those are our limits on z. Z always starts at 0 and always goes up until it hits this surface. So if you took a little vertical strip or vertical line segment or vertical, horizontal line segment and then raise it vertically, it's always going to go from the bottom there to the top, and they're bounded by those surfaces. Now, what we do is we take this and project it down onto the xy plane, and we get this triangle. Whoops, let's go back. We get this triangle in the xy plane, which I've drawn out over here, so you can see it where it's not, where you're looking straight down at it. And we look at that. Now draw a vertical strip here from lower y to upper y. And the lower y is always bounded by this curve, y equals 1/4 x. That's along this side here. What about this top one here? Well, the top one turns out to be negative 1/4 x plus 2. It's always going from this point here at 0, 2 to this point at 4, 1. By the way, you see that point, remember, we worked at finding these points out earlier. That point 4, 1, 0, projects to itself. That's 4, 1 in the xy plane. This point over here is 0, 2, and then that point is 0, 0, and everything else is projecting down inside that triangle. Okay, so we have this little, little isosceles triangle here. Okay, so we just need to find the equation of that line. Well, we know 2 points. It's pretty easy to find the equation. Notice that we're going to the right 4 and down 2. So the slope is negative 2 over 4. I'm sorry, I said that wrong. We're going to the right 4, but we're only going down 1. So that is negative 1 over 4 for the slope. And the y-intercept is 2. So it's just negative 1/4 x plus 2. Okay, there we go. So we know that that's the upper limit, and then this is the bottom limit for the second integral. Now project this down onto the x-axis, and we see the x's all go from 0 to 4. So see how we're projecting each time? Here we're looking at the full surface going with a vertical strip from bottom surface to top surface. That gives us our limits here in terms of x and y, but they're actually z going from this 0 to z going to this one up here. Okay, for z. Now for what about y? We project this down now. If z is our first variable to integrate with, we project it down onto the xy plane, and we look at what's going on there. Now we go from a bottom y to upper y, which is integrated with respect to y next, and it's consistently going from this formula 1/4 x to negative 1/4 x plus 2, and so those are the limits on the second integral. Then you project again onto the x-axis, and we see that x goes from 0 to 4. So notice the number of variables goes down. The first variable, the limits are potentially have x and y in them, no z's. Then the second integral, we've eliminated z by this time. These are y limits, but they have to be in terms of x. Once we've done that, we've eliminated y, and the last one are x limits, which are just constants. And finding the mass is exactly the same setup, exactly the same limits here, because that has to do with the domain. The only difference is the function you're integrating is different. Instead of the function 1 for finding the volume, we put in the density function, which was 4x here. And so, in fact, these integrals are going to work out very, very similarly. Let's do the details on the volume one first. You might want to actually try this yourself before you go on. If you do, you can pause this and come back. Okay, so here I've got it working out the details. You're just integrating the function 1, so the antiderivative is just z, and you're evaluating from between these endpoints, which are functions. Well, z is a constant here, 0, but up here we get this. So it's the top one, and then minus 0 is just this top function. So we get that. Now we're down to a double integral. We've already done a bunch of these, so this should be pretty straightforward for you. Find an antiderivative with respect to y. Take the negative 3/4 x, think of it as a constant, picks up a y as a factor there. This is a power function. Add 1 to the power, that becomes 2. Divide by the new power, makes the coefficient negative 3/2. That's a constant 6, picks up a y as a factor. Now evaluate that from lower limit to upper limit. Again, we're using the fundamental theorem of calculus. We did sort of a partial antiderivative. Take that, plug in the negative 1/4 x plus 2 in place of y. That goes in here. Here, we'll square it, and in here. Parentheses around that whole mess. Minus the same thing, but this time in the parentheses, we just put in 1/4 x here, here, and here. All right, now we get a little algebra. Okay, let's see if we can chase through. Very easy to get mixed up in all this algebra, but let's see if we can trace through without making a mistake here. Negative 3/4 x times negative 1/4 x. Well, first of all, x times x is x squared. Two negatives multiply to give a positive. Multiply numerators, multiply denominators. That's 3/16 x squared. That's not too bad. Multiply by 2. The 2 cancels the 4 down to 2, so we got negative 3/2 x. That takes care of the first part. All right, now this next part we're going to square and then distribute a negative 3/2. Okay, when you square a negative 1/4 x, you get 1/16 x squared. 1/16 times negative 3/2 is negative 3/32, and that's x squared. All right, for the middle term, when you square this out or FOIL it, you get, you get twice the product. So 2 times 2 times 1/4 is 1, but it's negative, so you get negative x for the middle. Then we have to multiply by the negative 3/2 and make it positive 3/2 x. The last term, we just square the 2, 4, to get 4. And then we multiply that by negative 3/2 to be negative 6. So we've taken care of this far. Distribute the 6 here. That's negative, let's see, a 2 cancels. That's negative 3/2 x. 6 times 2 is 12. So we got that part. I'm going to distribute the negative and do the multiplications here as well. So let's see, a positive, a negative, a negative. That's going to be a positive term. 3/4 times 1/4 is 3/16. X times x is x squared. So that's 3/16 x squared, positive. All right, here I've got a square that's positive, a negative that's going to be a positive term. It's an x squared term. 1/4 squared is 1/16 times 3/2 is 3/32. So that's positive 3/32 x squared. All right, that negative is going to make this last term negative. Cancel a 2 out, we get 3/2 x. So it's negative 3/2 x. Okay, so now, all right, we got all that. Let's do a little cleaning up and combine like terms. So the x squared terms, we have to just add them together. Let's see what we've got here. 3/16. Let's see, let's start with this one. Positive 3/32 x squared plus a negative 3/32 x squared just cancels out. That leaves the other two terms, which are both 3/16 x squared. Add those together, you get 6/16, which reduces to 3/8. That's the coefficient of your x squared. So you got 3/8 x squared. All right, how about the x's? I see a negative 3/2 x and a positive 3/2 x, so that cancels out. And I see another negative 3/2 x and another negative 3/2 x. That's negative 6/2 x, which is just negative 3x for the middle term. And I see negative 6 plus positive 12 is positive 6. Okay, well, all right, we had a little bit of algebra to do there. Yeah, granted, it's just algebra 1, but it's, there's a lot of it there. Okay, and then we do our polynomial antiderivative, which is not too hard. Let's see, we add 1 to the power, that becomes 3. Divide this by 3, cancels the numerator, so it's 1/3 of the 3/8 is 1/8. So 1/8 x cubed. Power goes up to 2 on this term, divide by 2, it's negative 3/2 x squared. And then plus 6x. The constant picks up an x. And evaluate from 0 to 4. Just plug in 4 everywhere, minus what you get when you plug in 0 everywhere. All right, 4 cubed. That's 4 times 4 times 4, or 4 times 2 times 4 times 2. The 4 times 2 is 8, cancels here. So you're left with 4 times 2 is 8 in the numerator. 4 squared is 16, divided by 2 is 8, times negative 3 is negative 24. 6 times 4 is 24, so those cancel, leaving 8. The rest of it's 0, so 8 is the answer. Now, there was an easier way to find this volume. We didn't really have to use an integral. If you can remember a basic formula from high school geometry or middle school geometry, the area of a pyramid like this is going to be the area of the base times the height times 1/3. Now the height is this side right here, since this is a right angle. So this side has length 6. And what is the area of this base? Well, there it is there. It's 1/2 this little base times this altitude going from here to here, which is just 4. So what is the area? Let's see, we got 1/2 of 2 times 4. So that gives you an area of a base of 4 times the height of, let's see, this is 4 and this is 1/2, okay? So let's see, 1/2 of the 2 is 1 times 4 is 4, so area base is 4 times the height of 6. Okay, so you got 4 times 6, but then you do 1/3 of that, that's going to give you 8. And so there's the details of that worked out. And of course we could check it with a computer algebra system calculator, and sure enough, there we go. Remember, the function we're integrating is just 1. So that's the volume. Now it turns out the density is very, very similar. In fact, almost all, I was able to pretty much copy most of this and just insert a few other things. So it's the same thing here, but we just have 4x for the integrand. But that 4x, the 4 is a constant, so it can be brought all the way out front. And the x is treated as a constant on the inner two integrals, so it can be brought all the way out to here. So from there all the way down to this point right here, it's exactly copied from the previous screen. So I'm not going to go back over that. Actually, all the way down to here. So if you look, 3/8 x squared minus 3x plus 6, that's exactly what we had right there. So all those steps are the same, but now we have to multiply by 4x before we go any further. So I'm going to go ahead and bring the 4 back inside and distribute. Let's see what happens. First of all, the powers all go up 1, so they're cube, square, and first power. And the 4 and the 8 cancel, leaves that to be 3/2. 4 times -3 is -12. 4 times 6 is 24. Now we do our antiderivative. The powers go up 1, divide by the new power. So that it goes up to power 4. Divide by 4, that's 3/8 for the coefficient. Power goes up to 3 here, 12, -12 divided by 3 is -4. Power goes up to 2 here, 24 divided by 2 is 12. Evaluate from 0 to 4. Plug in 4 everywhere, minus plug in 0 everywhere. Don't forget the parentheses here. All this in the last part is 0, which is kind of nice. And we just got to work out this first part. Let's see, 4 to the 4th again is 4 times 2 times 2 times 4, so it's 8 times 8. Cancels the 8 here. 3 times 8. No, wait a minute. 4 to the 4th. Okay. Yeah, so it's 4 to the 3rd times another 4 square times another 4 square. So the 4 square is 16, divided by 8 is 2, times 3 is 6. The other 4 square is 16. 6 times 16 is 96. Okay. 4 to the 4th, which is 256. 4 square is 8 times 12. 4 square is 16 times 12 is 192. The rest is 0. Combine just add those together, and you get 32. At some point, you could, you might just do that. Even with just arithmetic calculator, you could put in that last part. Of course, if you've got a CAS calculator, you can do the whole thing on the CAS calculator like you see in the upper right. Sure enough, it's also 32. So putting everything together, we found that the volume was 8, some cubic units like cubic centimeters or something like that. The mass is 32. That would be some mass unit like kilograms or say maybe grams, say 32 grams, 8 cubic centimeters. And the density, the average density then, is just found by just dividing the mass by the volume, the overall mass by the overall volume to get the average density, which is just 4. And that would be, say, if the volume was in cubic centimeters and the mass was in grams, this would be grams per cubic centimeter. I didn't really provide the units here, so we don't know what they are. All right, so now you have seen an example of how we should set up a triple integral. And it gets a little more difficult than double integrals because you have to visualize this 3D shape a little bit. But mostly it's just more of the same. It generalizes very nicely. But the problems do get longer, right? There's a lot more algebra. There's more steps to it. There's definitely more places you can make a mistake. So really attention to detail and being very, very careful on each step, it becomes very, very important because it's very easy to make a little mistake somewhere in the middle of this process. But the basic concept of it is really not any more difficult than a double integral. All right, so hopefully that's a good introduction for you. Come back for more videos later.